This is part 2 of module 3 based on chapter 3 of your Chengel ebook. Just a summary of what state your working fluid is in. Let's say you're given pressure and temperature, which under normal circumstances are two independent intensive properties. So like in the lecture this morning, you may check up on the pressure table, saturated pressure table, or the saturated temperature table. So here, let's say you're given P and T, and you're looking at the pressure table. I like pressure table. Yes. You compare the given T with the saturated temperature at that given P. If it is less, then you have subcooled liquid. Now, if you choose to look at the temperature table, you may compare your given P with the saturated pressure at the given T. If it is greater, it is compressed liquid. Subcooled liquid, compressed liquid, or just plain liquid, they are the same. That's clear. What's not clear is when you start falling onto the liquid, saturated liquid line, or in the saturated liquid vapor mixture, or on the saturated vapor line. You check your T against your saturated temperature in the pressure table, or your P, the given P, is equal to the saturated pressure at the temperature table, and they are equal. So you realize you are saturated liquid. But wait, it is possible that your working fluid may be wet steam, because at that state, your temperature is equal to the saturated temperature at the given pressure, or your pressure is equal to the saturated pressure at the given temperature. The same with the saturated vapor. So basically, these three states, they occur at the same temperature and pressure. I'll show you on the line in a minute. Another clear region, besides the subcooled compressed liquid, is the superheated vapor region. So you're given pressure and temperature, and you check out on your pressure table. The given temperature is larger than the saturated temperature. You have superheated. It's larger. Okay. But if you're looking at the temperature table and your pressure is less than the saturated pressure at your given pressure, it's still superheated vapor. So depends which table you are looking at. I prefer pressure table. Maybe you are more comfortable with the temperature table. Okay, let's have a look at the PV and TV diagram, which I did show this morning. So let's say given PA and TA, it's not marked here. If you if you check on the pressure table, at any given pressure, there is the temperature where your liquid starts to vaporize. So that's T set. So if your T is less than T set, say here, then you have subcooled liquid. If your T is greater than T set, you have superheated. But if you have your T is the same as T set at the given pressure, you could be here, saturated liquid, or anywhere along that line, or saturated vapor. So P and T in this region, on that line, are two dependent properties. You need another independent intensive property in order to get the rest of your properties, according to the state postulate. The same goes with the TV diagram. So you can check that one out. So anywhere along the red dotted lines, P and T remains unchanged. So your state could be either saturated liquid or saturated liquid, saturated vapor mixture, or saturated vapor. So you need a third property. Now during vaporization, this line, this red dotted line, a substance exists as part liquid and part vapor. We call it wet steam, both being saturated states. So to determine where exactly your saturated state is, whether it's closer to the saturated liquid line or closer to the saturated vapor line, you need what we call the quality, defined by mass of your vapor in the total mass of your liquid vapor mixture. Right? It's given in equation 3 in your ebook. Yeah. So quality is an intensive property. It does not have any meaning outside the wet region. So whether it's a subcool or compressed region or the superheated vapor region, it has no meaning. It only has a meaning within the dome. It is equal to 0 on the saturated liquid line. And this is all liquid. Is equal to 1 on the saturated vapor line. That means your vapor is 100% vapor. And it's somewhere between 0% and 100%. Between here. Between 0 to fraction below 1. Yeah. Besides water table in your appendix, you may also find properties of refrigerant R134A. This is a short-term solution towards a more environmentally friendly world. Yeah, it's given in the appendix. Later, even now, more environmentally friendly refrigerants have been introduced after the Montreal Protocol, 1985-86. Yeah, what is Montreal Protocol, or have you heard of Kyoto Protocol? You may check them out. As engineers, have to know about this because these are global efforts towards a more environmentally friendly refrigerants. Yes. Now, for water at 22.0.9 megapascal and 374.14 degrees C, there is no vaporization process. This is the critical point. Yeah. This is where the saturated liquid and saturated vapor states are equal. For water, it occurs at 374.14 degrees C and about 22.09 megapascal. Yeah. So you can check that for water at 40 megapascal and 20 degrees C, heated in an isobaric process, there will be no phases present, no two phases, just a single. Check it out. You can check it out. The process line I have explained this morning. Yeah. And I've given you some examples also this morning. From the property table, you may get, as I mentioned earlier, your internal energy and your enthalpy. To get the internal energy in kilojoule, you have to multiply your specific internal energy by the mass. Same goes with the enthalpy. What's given in the table is a specific enthalpy. You need to know the mass of your system. Yeah. For non-tabulated results, you have to interpolate. That means if the pressure given is not exactly provided in the appendix, say between 2, say 2.5 is between 2 and 3 kilopascal, then you would have to interpolate to get all the rest of the properties. Now, what if the quality of your wet steam is not provided? Can you determine it? Well, if you are given pressure or temperature and another intensive property, say for instance specific volume, yes, you may. You can look at 3.4. Yeah, from here, you can see that you may get the saturated liquid specific volume from the table if you know the pressure, and you can get the VFG, which is just the VG minus VF, yeah, and V average is given. You may determine your quality, and from the quality, you can determine other properties. Yeah, let's say if you have given Y average, where Y can be V average or U average or H average, the quality of the vapor can be found. I'll give you an example here. That is calculate the specific volume of saturated steam at 200 degrees C with quality of 70%. You can do that with a U and H. Yeah, if you can find specific volume, then you can, of course, determine the specific internal energy as well as the specific enthalpy. Yeah. Now that goes for liquid, vapor, and liquid. How about gas? Okay. So for gas, it's the vapor above critical temperature. The property variations with temperature and pressure may be obtained with equations that relate the properties. Now, you no longer need the pressure table and the temperature table. So, any equation that relates the pressure, temperature, and specific volume of a substance under equilibrium is called an equation of state. The simplest being ideal gas equation of state. I'm sure you have seen this in your high school. Yes. P multiplied by the specific volume is equal to RT, and T, mind you, is in Kelvin. Many students in past have made a mistake of not changing the Celsius into Kelvin. It's a huge error there, careless mistake. So the rest are given. You have seen this before in your high school. You should. If you have not, you go please check it out in your high school textbook or anywhere online. Yeah. So the molar mass of any gas may be obtained from the appendix. This is given here. Yeah. Now from equation 310, PVRT, it can be written in several forms, but the most frequently used one is this one, PVMRT and the PVRT, where V is a specific volume. So you see here, how do you use that equation? Let's say you have a piston cylinder arrangement, but this time your piston is fixed. Means whatever happens to the content, the piston cannot move. So you have an isochoric process. Yeah. So if your initially you have your pressure, temperature, and volume and mass, and after it's heated up or cooled down, in this case heated up, you measure your pressure, temperature, and volume, mass. You can apply these two and you will get this mass being the same. So it's a closed system. And in this case, if your volume remains the same, then V1 is equal to V2. If you know P1, T1, and P2, you can get T2 or any one of those variables if you know the rest. Okay. But an ideal gas is an imaginary substance. It doesn't exist. Real gases follow 310 at low densities, low pressure, and high temperature relative to its critical temperature and critical pressure. Yeah. Air, nitrogen, oxygen, hydrogen, and even heavier gases such as krypton can be treated as ideal gases with negligible errors, about less than 1%. Yeah. Water vapor and refrigerant vapor like R134A coolants are not to be treated as gas. So for these properties, you need to check out the property tables. They must be used. You cannot use the ideal gas equation. See, here is the map. See, remember the dome? I told you if it's gas, it's here. You don't need the dome to identify the state of your gas. As long as if it's a PV diagram, the constant pressure line crosses the constant volume line, crosses the constant temperature line, you can indicate the state of your ideal gas. Yeah. So it is convenient to use 310, but only under certain conditions it is acceptable. Low error, that is at very low pressure and in any temperature, gases behave like ideal gas. Okay. The deviation, under other events, can be corrected with the correction factor. We call it compressibility factor, Z, which is defined as PV/RT. For ideal gas, Z is equal to 1. You can see that, 317, 319. The further away Z is from unity, as less than 1 or more than 1, the more the gas deviates from ideal gas behavior. Okay. And gases behave differently at any given temperature and pressure, but their behavior is the same at reduced temperature and reduced pressure, defined as in 320. Okay. So the Z factor is almost the same for all gases at the same reduced temperature and reduced pressure, with the generalized compressibility chart applicable for all gases. You have that in your appendix. You can check that one. So if you know the reduced pressure, you can check out the Z, and then you can get the other properties. Okay. Just note that at very low pressure, there is reduced pressure less than 1, gases behave as ideal gases regardless of temperature. At high temperature, that means reduced temperature greater than 2, ideal gas behavior can be assumed with good accuracy regardless of pressure, except when PR is greater than 1. The deviation of a gas from ideal gas behavior is greatest in the vicinity of the critical point. Yes. In the vicinity of the critical point, yes, is behave far away from ideal gas behavior. So you have to be careful. There are other equations of state, but in this class, we're just going to look at the ideal gas equation of state. But to know, there are Van der Waals equation, Beatty-Bridgman equations, and Benedict-Webb-Rubin equations. They have less limitation than the ideal gas equation of state. That wraps up module 3 based on your chapter 3 of the ebook.